that problem because parties of the physics department, especially when there's 95% men, they don't tend to be too exciting until we found out that.
So this is the Odd Engineer podcast. I'm Erin McDermott, your host, and we are here with a very special guest, Julius Muschaweck. He is the other Illuminations guy on Odd Engineer that you can book time with, but we've put him into an even smaller niche as being the LED Whisperer and Colorimetry Pro. And he's over in Germany right now, and he is the Geschäftsführer. You're the CEO of your own freelancing company, JMO.
Yeah, it's just, yeah.
Do you call it JMO GmbH?
Auf Deutsch, yes. Auf Deutsch, it's JMO GmbH, but you know, it's just the company which I created to run my business. In fact, it's just me, and I'm a freelancer back again. So I think I'm good at a few things.
Yes.
But having a boss is not one of them. So just being a freelancer and just doing my own thing is my favorite mode of operation. And then I'm free to choose to work on the projects which I like, and of course to work with the people who are responsible for that and helping that. So that's it. But you know, to be in a structure that just doesn't let me do the things I would like to do is not so good for me. So this is just good for me.
I totally understand. And you know what? I think that a lot of people who start out their careers studying physics tend to be in that vein a little more than the average engineer or scientist. And that's how you started out, right? You have a physics diploma.
I'm a physicist, yeah. I'm a physicist. And I think a good physicist should be, through his whole life, just, something like a curious kid. Always curious, always eager to learn new things, and always, mentally ready to be truly and fundamentally surprised, and just taking nothing for granted. Yeah? And so, and I wanted to learn things and understand things on a deep level. So that's why I studied physics. I then found out that I don't necessarily learn all of that at university. But that was the start. Yeah, I studied physics in Germany.
But then how did you get into the smaller part of physics that is optics?
I wanted to do something that actually would, improve things a little bit. So things like, doing things for defense work or for nuclear or this kind of thing was just not my thing. And I also just wanted to do not something that I would do in a lab, not being able to explain anything to anybody. And it's fascinating. I have friends who are particle physicists, and it's just so amazing what these guys are doing, but I don't want to be one of them. I want to
Their
do
dinner
something.
Party conversations are so boring, no one can understand.
When we studied physics, we had that problem because parties of the physics department, especially when there's 95% men, they don't tend to be too exciting until we found out that the German students, they're like 80% women, and they had the same problem, just the other way around. So those two departments, those two faculties, we decided to do our parties together, and then that was great.
Problem solvers.
Well. Yeah, so we solved that problem, and I was lucky to find that there was a professor and an institute that was working on solar energy at the time. So
that's a long time ago. Sorry, I don't mean to date you, but
that was around 1990 and 1995. Yeah. So
that's like at the start of.
So actually, when I got into that was around 1986, 87. And yeah, and so I got there and got involved with solar. That was great. And then I did my thesis for some solar collector testing that was solar thermal, that had just little to do with optics at that point. And then that was bad times in Germany, bad times of physicists. It was 1990, the fall of the Iron Curtain and the unification of Germany. And one of the things they did is they dismantled the National Academy of Sciences in East Germany. And all of a sudden we had 20,000 unemployed physicists on the market. So my dad is an architect. And so he said, before you do something else, let's build something. So I was a real estate developer for 5 years.
What?
Yeah. Yeah. And I found that, being a physicist just is very good education for almost everything, because they let me do the numbers. I was the only guy who could operate a computer. So they let me do all the the paying and the accounting, this kind of thing. But my major thing was to do energy concepts for those buildings that we made. And we built them to much higher energy standards than were usual in the early 1990s. So that was great. But there I found out that at my heart, I'm not a real estate developer. I'm just a curious kid. And I wanted to go back to science, and I had a chance to go back to that same physics department and the associated semi-private, semi-public research institution. And there I got into touch with optics, because the idea was to make high-temperature solar collectors that would just rest on the roof with no moving parts and create heat at 50% efficiency at 180 degrees C, 350 Fahrenheit.
Wow.
And a flat black plate just won't be sufficient. So we needed vacuum tubes and black absorbers with selective coatings and some mirror reflective troughs around them to collect and concentrate the sunlight. And that was interesting, and I thought it would help. And I thought, the optics part would be easy, just bend a little reflector and do some pocket calculator things. Okay. That was 25 years ago, and I still learn new things about this deep, beautiful topic of light and thermodynamics every day. It is just so fascinating. Yeah?
Yes.
And this is how
solve the problem though with the.
Oh yeah. We built this world record collector. Okay. And we built the first version of it here in Munich. And then I reported that in a conference, and Roland Winston became aware of me. And for the guys who don't know Roland Winston, maybe you heard the buzzword non-imaging optics somewhere. Mm-hmm. Roland is sort of the founder of that field, because he's a particle physicist, and he needed non-imaging optics to concentrate the faint light from Cherenkov radiation onto his photomultipliers. And finding that there was no established theory out there, he just did what good physicists do. He did it himself and reinvented. Of course, he reinvented many wheels, but he was the guy who actually made non-imaging optics a field in optics. So
I just thought it was what you throw everything that's not imaging into.
No, he's a brilliant physicist, but he is not very good at marketing, I'm afraid. Because otherwise he would know that you should never name something by what it cannot do. But he was the founder of the field. He had the privilege of giving it a name, and unfortunately he chose non-imaging.
I didn't know.
And I'm not sure, I don't even know that if there's a better name for it, but it actually is about the optics of concentrating sunlight. And then I spent a year with him in Chicago, and actually we built this world record collector at the time, but the world wasn't really ready for it. It was just too early. And that's where I found, and a couple of colleagues also found, that solar energy is important, but it's over-researched. It was over-researched and under-executed at the time. So we decided to just turn the light path around and use our insights about optics to do optics for illumination. And this is how I got into illumination optics. We founded this great little company called OEC here in Munich. And just, it was really almost, Steve Jobs style. Huh? We decided to go back from Chicago and found a company, and we founded the company in Harold's guest room. And then published some papers and went to some conferences. And we didn't really have a business plan. We just figured that we know what we're doing, and we had the great luck to be just right there with this odd idea of doing engineering for optics, for illumination optics, which was not something that people would do at the time. There was no software, so we were writing our own software in the beginning.
Yes, I was going to ask, because to be there at that time, what year was that when you founded that company, by the way?
1999.
Oh.
In 1999, there was ASAP for Straylight, and Light Tools was in its infancy.
It existed then? I didn't think it even existed.
Yeah, but not in a version that anybody would think worth buying a few years ago. That's different now, but by that time it was really just, it was just something they tried and was very successful later on.
And the computing power didn't make it feasible, really.
Right. So, but all that come together. The computing power became feasible, and then came the LED revolution, which started around that time. And when we founded OEC, we were not aware of that.
You had some good luck. You were just right there waiting for it to fall out of the sky.
Yeah, but that's how it works. Isn't it like that? All the good things in your life happen by maybe something like active waiting, not making them happen.
Active waiting. I like that.
But just putting yourself on a spot where interesting things might happen, and then be in a state of mind to just, grab it. So you're walking along the path and you don't look so much at the horizon and the far goal. You just walk along, and then you find this golden nugget at the edge of the path. And when you're ready to pick it up, you can pick it up. So
I love that. Yes.
Yeah. So that's kind of what we did. And then we created this company, and we did some great work for illumination. But it was not just engineering. There was also like a freeform optics research institute.
You were doing freeform optics back then too?
So the first paper in the OSA database with freeform optics in its title was written by Harold and me.
Get out of here.
Yeah.
Wow.
Tailoring freeform optics for illumination. That's our 2001 paper. And that was actually, we were not the first ones to do that, in fact, but we were the first ones to put that into a really usable implementation.
That's what matters.
You could actually, we could actually design freeform optics. Nobody could make them at the time. But that changed quickly. And then, so that's where that started. So we did that for a while. And then, up to that point, I had been at university and in a totally different business, but also as a freelancer. Real estate developers are also typically freelancers. And then we were, these freelance scientists doing this kind of thing. And I felt that I don't know enough about industry, and I am too distant from things that are actually being made. So one of the things we did some great freeform optics about one of these little machines that mostly women use to pick, this rotating wheel with tweezers, which would rotate and pull the hair out of legs and other parts of the body. Yeah,
that sounds terrifying.
And but it actually works quite well, because the hairs don't grow that much as when you shave them. But okay, let's not get into that. But the company wanted to have freeform optics to illuminate the skin, so you would know where you would drive the machine. So we did freeform optics for this machine. They paid us a lot of money for that.
That is so weird. That's what you get when you're freelancing, right? You get to play with weird stuff.
Right. So one and a half years later, we found that they actually made that product for the market. And but that was, I felt, estranged. I was doing things and I would never hear about the results. And I wanted to join a company that would actually make things. And so I left that company, and the others continued and were quite successful for a number of years. But I joined Osram. And Osram is maybe not so much known in the United States, but it's one of the largest LED manufacturers on the planet.
I'm quite familiar because I used to work for Valio Sylvania, which was part of Osram.
Part of Osram, and the guys who are in the business, of course, they know Osram, because when you want to have good LEDs, then Osram is one of the companies that makes them. And
yes, if you're in the automotive lighting, then you probably know Osram, but otherwise you probably know Osram.
Yeah. Anyway, it is a company that makes things by the billions, because Osram makes billions of LEDs. and I thought optics is so all important. And then I learned that when you make things by the billions, then maybe process control is important. So I learned a lot about that, and it was just great. At that point, Osram is a company that made light sources. So they were never really worried about optics, because optics would
someone
be
else's problem.
Yeah, right. Huh? It's an SEP and somebody else's problem. Did you ever read the Hitchhiker's Guide to the Galaxy?
No.
You probably should. It's a great book.
SOP was just standard operating procedure, but apparently it's also
it's SEP, as somebody else's problem. So Douglas Adams, he wrote the science fiction novel Hitchhiker's Guide to the Galaxy. And one of the things he's saying, it's so hilariously funny, the whole book. And one of the things he's saying is, of course, there is no technology to make things invisible. It's just not how physics work. But what works is to put what you want to disappear into an SEP field, which is a somebody else's problem field. And then this pink sofa is just something that stands there, and everybody could see it, but they see it, but they don't notice because it's somebody else's problem.
And that
was optics for Osram at the time. And but they found out that they have to care more about it, because customers had problems with using LEDs in a proper way. So they wanted to understand more about the optics, and also about the lenses they would put on LED packages themselves and so on. So that's when I joined, and I just learned so much about LEDs in my 4 years in Regensburg. It was great. It was a great time. It was also great fun to create the optics department, application engineering there. And so I was there, and then I went to corporate technology at Osram and became like at that time, Osram found out that they need a credible expert career.
A credible expert
career path for people like me who know their stuff and really want to move something, but who should not become managers, because it would be a waste of their talents, and they probably would not be good managers. But in many companies, that's the only way to get promotions, right? And so Osram did it the other way. They created a career path, and because I was always, freely telling everybody what I know, I was like the role model for that expert career path. So again, I was there at the right time by sheer luck, and got promoted to be like the global coordinator for optics in Osram. So I had no budget and no direct reports, but I was still responsible for making optics work on Osram for Osram worldwide. And so I got the money and the people to create something like a worldwide community of optical engineers. So we had this Osram internal optics conference, and for years that was probably the hottest illumination optics conference on the planet, because there was enough critical mass in Osram, over 100 people doing illumination optics more or less full time. And because it was company internal, they could speak freely. And that is not something that happens at SPA in San Diego. You always hear great things, which was 3 years old. So it was a great time, and people were coming together, and then they knew each other, and we had this online discussion forum where people would ask each other questions, and because they were just bugging me too much, and then I created this forum and told them, okay, so ask me that question, I'll be happy to answer it, but only after you post it there. And then of course some improbable guy from Detroit, Michigan would answer the question from this other guy in Germany, because he was much more of an expert about that than I am.
That's interesting.
Yeah,
I mean, building community is very hard. So this is the great information for even beyond optics. Just how do you get all these people to work together? But you need a problem. The problem
you need a problem. You need critical mass, but you need the ability for people to speak freely, and that's what makes it so difficult out there. Right now, the world of illumination optical engineers, we estimate that it's maybe roughly 20,000, more or less full time.
How do you count that?
Because we talk to the people who sell the software.
Okay.
Yeah, and they won't tell you how much software seats they sold, but you can throw numbers at them and see whether they nod or shake their heads. Okay, so that's what we did, and I think 20,000 is a reasonable number, huh? And most of them are just working by themselves in their company. So most of them just develop the illumination optics part for the bigger products that companies make, and they just need this odd Joe or Jack or Evelyn or Aaron or Julius to take care of the optics. And then these guys and girls, they found out how hard it actually is to get things right.
Yeah.
But they are not
And a lot
allowed
of times
to.
they're not even optical engineers by training, right? They're electrical
Right.
engineers or mechanical
Electrical engineering or physicists or computer scientists. Huh? And even if they are optical scientists, then they probably learned imaging optics.
Right.
And that, but light doesn't care why you send it through a system, but when you want to make it good, then you need to think differently about light in illumination. Huh? And
yes.
you know, I know that, you know that, but not everybody out there knows it. Huh? And
yes,
and
I mean, even optical engineers will say, well, light is light. Yes, that's true, but there's a totally different way to design and think, like you said.
It's a different way. You need to think about light in a different way to get to achieve good optical designs for illumination. That's just what it is. And so we did that at Osram, and it was great. But then again, you know, Osram is a company that had a relatively small LED department within a big lamp company. And Osram for decades was making lamps using glass and metal. And it was always the same structure, always the same customers, and always the same competitors. And the entry barrier for you to make a glass bulb, for an incandescent bulb, is billions of dollars. And then you start making things and you don't have all this, you know, experience to get it, you know, automated and cheap. So nobody would become a competitor for Osram for decades. It was Philips and General Electric, and that was about it. And then and then comes the LED revolution, which is not just a different technology. It's a game changer, because then all of a sudden, some people in China buy LEDs, buy a pick and place machine, and hire an electrical engineer, and then come up with a light bulb replacement. Okay, and Osram was not in a good shape to cope with that new animal on the planet. And then it was difficult for Osram, and I also felt that I sort of had my job done. You know, I started out at Osram when I was one of maybe really 4 or 5 optical engineers in 2006. They just didn't have that at Osram at the time. And when I left, we had over 100 people, and they all knew each other, huh? And we're working together. So in a sense, they didn't need me anymore. Huh? And then it was time to go. And
your
my
babies
first
grew
boss,
up.
yeah, my babies grew up, and it's just to love to watch things and people and in groups grow. So I drank a beer with my first boss at Osram again, and because, you know, we always kept in touch, and drank a beer every half year or so. And at that time, Markus Zeiler, he had just joined ARRI. And if you don't know ARRI, you're wrong, because you do. If you ever watched a movie that was nominated for an Oscar over the last 6 or 7 years, then with like 95% probability that movie was shot with an ARRI camera. They are really the kings at the high end of this market, and they're also making lamp heads. So I joined ARRI as lamp heads for the movie industry. Yeah?
What are lamp hats?
A lamp head.
Head. A lamp head.
Like a luminaire or a Scheinwerfer. Huh?
Scheinwerfer.
That's how they call it. A lamp head.
Oh, I didn't know. So, I don't know that industry.
Yeah, but anyway, that's how they call it. These things that have, you know, that look like that, like a big tube, which have like a plug on the backside, and light is coming out from front and illuminate faces like yours to make the actress and actors look pretty. So that's a lamp head.
Okay.
And ARRI is making them, and I was helping them to make them. And then at ARRI, I got into the medical industry, because Ari thought we need to diversify. Where can we put this beautiful sensor that is creating award-winning skin colors, and and creating the best pictures? Yeah.
I know
So
a place we can stick it.
So they thought, okay, so let's diversify, and then they found that in the medical market, surgery microscopes, 3D surgery microscopes, which surgeons use to make really tricky operations on tiny things, like replacing the bones in your middle ear.
Wow.
Yeah.
What makes it 3D? Are there two different cameras?
There are two cameras, and so the standard way of doing it is to have a microscope, like a stereo microscope, but it's really stereo. It's not like a microscope which would split the 2D image into two pairs. It would be really like two pairs which come out in an angle. And that really makes things 3D, and they stand out, and you can see what you're doing in 3D with the magnification of maybe something like 4D, where you can see the details that you cannot see with the naked eye or with a loupe, but still not too much, so you can have this feedback. Then you see your hand moving without the instrument totally leaving the image because of magnification too high. So this is this intermediate thing, and Ari found that nobody is doing it fully digital. So they created this first fully digital stereo surgery microscope.
Oh, wow.
And they needed some guy to get the illumination right for that, and that was me.
Hey.
And that was fascinating. That was a great project, you know. And I got a chance to visit surgery rooms and watch surgeries, many of them, because I needed to understand. Oh yeah, one of the things I didn't mention in my career, that I was also a paramedic.
Really?
Yeah, but
what haven't you done?
I don't know.
That would be easier to interview that way.
That was around 1980, and so instead of going to the army, we had the draft in Germany at the time. You could decide to go to civil service, which I did, and part of the job was becoming a paramedic. But that was not your standard of paramedic. I was just, you know, like an extended first aid course. That was my education for being a paramedic. But I've been at some really creepy places and watching really creepy things, and I find that it shakes me, but only afterwards. In a situation, you know, you just function.
Wow.
And in a surgery room, the thing is different. It's not all full of blood and adrenaline and chaos and panic.
Yeah.
It's just this very
hopefully
quiet.
Not.
No, hopefully not. But, it's this quiet, concentrated work environment. And what they do is just they cut people open. That's part of the work. But it's actually much less bloody than you might think. And I could watch that, and it was just a fantastic experience to watch these surgeries and watch these fantastic surgeons do their thing and learn what they need to do good surgery, how the light must actually be. And that sort of, you know, that maybe also illustrates my general approach on things, that I want to understand the complete problem. Because if I don't, then maybe my local optics or LED driving and calibration solution won't be what the whole project really needs. So I did that for a while.
So wait, what's involved in illuminating that kind of tissue? Like, how do you test that? How do you simulate that? How do you know that you're going to have the right wavelengths and all the right illumination at all the right angles and stuff?
That's what made this project. No, it's not. No. Okay. And and if you ask me something that's secret, I'm just gonna tell you. I'm sorry, I can't tell you because it's secret. But that's not secret. Okay. The thing is that you know, many people are aware of the CRI, the color rendering index, which is an important topic for LEDs. Sometimes the light just looks very creepy. And with bad LEDs, and you know, white looks white, but this people look like corpses, and oranges and you know, tomatoes look like brownish, and meat looks rotten. So that's bad color rendering, and that's all well known. And if you do illumination for a purely optical microscope, where the surgeon sees the light through the microscope directly, then color rendering for that lamp head is probably a very good idea, to have a very good color rendering light source in there, just like you would do for general illumination, because then it just looks true.
And you use the same CRI color rendering index, because I know that there's multiple ones that they're playing with now. But...
No, and you shouldn't do that for a fully digital camera, because it is not the human eye which sees the light. It's the camera which sees the light, and the camera has a different sensitivity. And on top of that, you have, it is actually a little, computation intensive, and it needs to be done properly. But without too much of a delay, you can do quite complex computations on those images before you present them to the surgeon in the monitor, in the 3D monitor. And that is something that you can use. You can make colors which actually look not too good for the human eye, but which make the different types of tissues stand out in a way that you cannot possibly have with just standard illumination, because of the possibility to illuminate the tissue in a way that, if you know the typical spectral behavior of the tissue, and when you think of a surgery, it's all like, you think blood, but that's not true. Almost everything is just whitish or yellowish. So think of bones and sinews and fat and nerve cells and all these things. They are all more or less yellowish, and surgeons want to differentiate that, and they differentiate by surface structure. That's what you get if you do good illumination from small angles and everything. But they also differentiate by color. They see the subtle color differences, and it's possible, when you know the details of the spectral response of the tissue, to design spectral illumination in a way that makes those colors more separate than they would look like under normal illumination. And it wouldn't look too true or good or like you used to. But then you can compensate for that in what they call grading in the movie industry, when you change and modify and adapt the colors in the image. So you can make it look like real, except that this yellow is a little more yellowish than this other whitish, and which allows surgeons to differentiate tissue a little better. And that is really important, because when you do things like a cochlear implant, the cochlea is this little spiral that's in your inner ear. And for some people, the machinery in the middle ear is broken, but the nerve cells in the inner ear are still good. So what people do is they insert like a spiral with electrodes, and that is driven by a microphone and some electronics. Wow. And then that makes people hear again. And so it's really important to do that. But the surgery is tricky. Yeah. The surgery involves, to cut it open and mill away the bone until you get to this little slot where you put things in. And it's a dangerous place, because if you mill just a little bit too far in this direction, then you have broken the skull, and you're at the brain level, and then the two facial nerves are just there, and you have to find the hole in between them. And if you mill through them, then the person might hear again, but looks like that, so that's not good. And then if you go a little bit too far to that side, you are in the middle ear. And even if the machinery is broken, it would be like a jet engine just next to your ear, and all the nerve cells would be broken anyway. So it's really important to differentiate between this bone and this nerve and so on. And this is where this kind of good optical engineering, good spectral engineering of LEDs helps. So we used a 4-channel illumination. And yeah, it was actually warm white, cold white, red, and green. And then we had to mix that color together, and that is where things became tricky. This is where it's people tend to think about LEDs like you just, if you're in the electronics world, you buy a resistor. And if the 10% resistor isn't good enough, you buy a 1% resistor. And if that's not good enough, you use the laser trim 0.1% resistor. And you just, you buy it. And if you want more precision, you just pay for it.
Yeah.
And if you buy a screw, then you buy a 1-inch screw, and the 1-inch screw, the length is just doesn't vary by less than 1%. Not so with LEDs. LEDs are just different. They are, the light is created in a layer which is just a few atoms thick in the LEDs, and that's very tiny. And at that level, you have to get the chemical composition part, the fractions of the materials just right to get the right wavelength. And that happens in very low pressure at like 2000 degrees Fahrenheit. And so it's amazing they work at all, but maybe it's not so amazing that it's not like you make a screw or you trim a resistor. It is really more tricky than that. So LEDs vary. So you have to cope with the fact that you cannot just buy 121 lumen LED. You get something that varies, and it also varies with operating conditions. So I had to do an optical design which would do very, very good color mixing. And that's something that good optical engineers could do. And I'm sure that you could do it just like that. But the really tricky part was that to get the consistent light down there. So under varying operating conditions, and red LEDs react differently to temperature than blue LEDs, and that kind of thing. And then no two LEDs would be the same, even at standard conditions. So we had to calibrate them over the whole operating range. So that was the actual really tricky part of that problem. So that's what I did at ARRI.
Wow. And did the imaging sensor, because you said this was digital, did that play into that at all, or was it mostly on the image processing side that you had to work with?
It was about looking at the spectra and adapt the way we would. So when you want to fix a light source to a certain white point and a certain brightness, for us that's 3 numbers. Two numbers for the color and 1 number for the brightness. So you need 3 degrees of freedom to adapt that. And you can get any color and any brightness you want by having 3 different light sources. And everybody who is watching this video, or you right now watching your screen, you know that, because if you take a loop and look at your screen, you find red, green, and blue pixels, which do that. 3 sources create everything that's on screen. But here in our little machinery, we had 4. Warm white, cold white, and red and green. So we have 1 degree of freedom free. We could use that degree of freedom to select, to match the spectrum to the needs of the sensor, which was given with its red, green, blue sensitivities, and with the specific properties of the tissue to make that good. And it was some science and also some trial and error. And it was some work involved by people at ARRI who are just world-class graders. So the person who has been grading the Lord of the Rings has been helping us to do that.
Wow.
So that was just a fantastic experience, and
wow.
and that was the tricky part of getting that right.
Yeah, it sounds really complicated. So then
it was maybe the biggest challenge in my career to get that right. But in the end, we figured it out. It was great.
And that's the one you told me just before this interview. You're doing like a next version of that now. Maybe?
Yes, we're working on. So ARRI has split off that company now, so it's not part of ARRI anymore, which is probably good, because if you ever watch things on a film set, it is just so much improvisation, and it's fully okay if the lighting or whatever you prop up there, it has to work once, has to do that reliably, but once is just fine. It's not true for a medical instrument. It's not good enough for a medical. So the whole thinking in the medical industry, where nothing is improvised and everything is just very much standardized and tested and documented and everything, that is just a mindset which is so different that it's probably a good idea to just kick it off and then let it grow somewhere else.
That's a good idea.
So that's what Ari did, and now it's a separate company, and I left them after some time because, as I said, I'm just good at some things, but I just want to be my own boss. So we're still good friends, and I'm still working with them and for them, but it's now it's just part of me being a freelancer. So that's what I'm now.
So, and that was, you just left there right into your
I left Osram in 2013 to join Ari, and I was there for 5 years, and then in 2018 I left Ari, and since 2.5 years now I'm a freelancer.
Awesome.
And as a freelancer I do basically 3 different things. I do optical design for illumination for people and helping them with LEDs and colorimetry. And the second thing is I teach courses, and I used to teach them live in a classroom, but this is where COVID-19 gave me the last kick in the butt, which I needed to create online versions of that course, which are quite successful and which I just love to teach. It's really good to do it that way. And the third thing I'm doing now is to write things. So I'm writing a book on illumination optics with my friend and colleague Henning Rain. And that book we're just negotiating with the publisher right now, but the book is probably gonna come out sometime this summer or this fall. So if you follow me on LinkedIn, you're gonna be notified when it's out.
Awesome. That sounds great.
So that's the 3 things that I'm doing right now. And it's just great, because now I've been working hard to get into that position where I am right now, that I just can enjoy to know a few things and be able to pass it on to other people, and to just, sort of pick the things which I like to do most and just work my style. Mm-hmm. And my style is a little different from what many typical engineering companies are doing. So the typical engineering company that automotive manufacturer would hire to design a headlamp or a rear lamp or something like that. Those are companies who have great engineers on board, but they look for, like big projects with long runtime, and then they would complete the work and probably deliver great work, but they wouldn't tell too much about what they did and why they did it and how they did it exactly, because then the customer could be educated too much and they wouldn't be needed next time. Huh? And I do things completely differently. If I can help people in a way that they don't need me, mm-hmm. I'm happy.
Aww.
And so one of the things I'm doing is, and I really love doing, is just if somebody calls me for an hour or a few hours to just help. I've been doing this for 25 years now, and anybody who is doing his or her thing for 25 years smells bad in good directions.
Yeah.
You get this gut feeling, and this I like to call it some educated, rational gut feeling.
Yeah. Because you're German. Yeah. It can't just be a gut feeling on its own. It has there's reason behind it. I just can't explain it.
I tried to do that. Yeah. I'm German. No? We do everything, but we don't do jokes.
Wir können alles schaffen, aber kein.
Okay, just hold on a second. I think, let me brighten this up a little bit. Yeah. Okay, here we go.
You gotta fix your illumination there.
Yeah, the sun is going down and still shining a little bit through the blinds, and I have to make it a little brighter. So that's what I really like to do, to help people, and to have them throw their problem at me, and then I give it some thought, and then I typically can say pretty quickly, don't go there. It looks dangerous. Huh? Go there, huh? Because this road looks much more promising, and then I can do that based on some first principle feasibility analysis, and also just based on lots of experience and seeing things. So,
and getting that feedback really early in a project, and can help you make or prevent you from making big mistakes. For sure.
Yeah, and of course, they pay me by the hour, and I probably typically when they do that, I save them much more than then they would pay me. But that's just fine, you know, because they are taking their risks. They take all the money in their hand to pay for the complete development, and they have all the risk of, you know, making it a successful product. I don't share that risk, so I just want to make sure that they don't get hurt more than absolutely necessary.
So can you give us some examples of actual physical things for the people listening so that they understand if that's a project that would line up with something maybe they're doing, because they don't really understand, okay, what is illumination? But that would be like a headlamp or a downlight in a
let's look at this very simple example, deceptively simple looking example of like a headlamp. I mean, really a headlamp that you would use for not for maybe for doctor, but for outdoor hiking.
Okay.
You know, in the medical industry, they understand lux and they're much more technical. But these outdoor people, you know, I've been doing that, and I was just would like to recount the experience. So this company came to me to develop optics for that headlamp. Okay, and then I asked them, okay, so what are the specifications? And they said, well, the lighting, they actually speak of a lighting distance. How far does the beam go? And they said the lighting distance should be 600 feet. So that's kind of odd for a physicist, because when I have that headlamp on my head and I look up to the sky, then the distance this beam will travel is roughly 13 billion light years.
Editing Aaron here. At this point in the interview, we reached some technical difficulties. My computer crashed, and I thought that the first part of the interview was lost and gone forever, but it wasn't. We have it, as you can see. So we ended up doing the rest of the interview as a speed version of a complete interview, but we covered a lot of new ground, so I'm just gonna throw that in right here. Enjoy.
Oh, no problem. So we just start from scratch?
Yeah.
Okay.
So I'm Aaron McDermott, your host of the Odd Engineer podcast, and we're here with Julius Muschaweck, who is our illumination expert besides me, but we put him into a smaller niche of the LED whisperer and colorimetry expert. He's going to tell us all about his background experience and why you would want to book with him on oddengineer.com. Julius, thank you for being here.
Thank you for the invitation. I enjoy talking to you, Aaron.
Since we already did this interview already and my computer crashed, but let's.
But shit happens, doesn't it? Yeah.
It does. That's part of engineering too.
Yeah.
So let's.
So you better get used to it. and learn to cope with it, and that's what we're doing, aren't we?
Absolutely.
Yeah.
So the people out there who are listening, they might not really understand what our type of optical engineering is, or colorimetry, or working with LEDs like we do. Can you maybe just give us your basic elementary description of what you do?
Of what I'm doing, I'm helping to bring people light where they need it and how they need it. That's basically what I'm doing. So people want to illuminate something for whatever reason, and typically just hanging a light bulb in a room is not going to be good enough, and so we need to do some more, and that more might be to put some optics in front of the light source and choosing the right light source in the first place, and then driving the light source in the right way, which is amazingly tricky when it comes to LEDs. And I know a few things about that because of, like 25 years of experience in that field. And so that's what I'm doing. I'm helping people to bring light where they need it and how they need it.
And that could be with LED sources primarily, but also
primarily,
other types of sources.
Yeah. So I'm not picky. If somebody wants another source, no problem. Huh? And when you want to make a lamp head for the movie industry, and you want like an electrical power of 18 kilowatts, those are cables which are that thick. Huh? It's not like your normal wall plug. Really, it's like 180 full power light bulbs. And then if you want this kind of power, then LEDs are not your choice. You need a high intensity gas discharge lamp, but you also need optics to get it there. So whenever you watch a movie and there's this scene in the saloon and the sun is setting and the low sun is shining through the windows, and you have this little haze in the room, so you can see actually the beams go through the window, and it's just this very this atmosphere which is sometimes creepy or dangerous or just nice and cozy. Whatever it is never the sun. It's always these big lamp heads. Okay.
Wow.
And you just can't really do that with LEDs at this point. So whatever light source it is, it's just where we just take it. So that's what I'm doing.
Yeah. So can you also explain then colorimetry and what that means? Because lately I've gotten a lot of requests for people who are asking for help they're building a device where they're using color to figure out what some material is, and then they see you on Auto Engineer and they're like, oh, colorimetry, he's the guy I need. I'm like, actually, maybe the spectroscopy expert is more what you're looking for. So for those people who are kind of confused about what that term colorimetry means, what is that actually?
I think you cannot really separate color and colorimetry from thinking about spectra. So that's what's actually at the bottom of it. A spectrum is like the colors of the rainbow. You just know exactly how much of each color of the rainbow you have. But then we humans, we cannot see all colors of the rainbow. Our eyes are limited to basically 3 different color channels. And if you take like a loop and look at the screen in front of you, then you can figure out that this is actually true, because what you're going to see when you look closely is just an array of red, green, and blue pixels. And all the colors on the screen, including white and everything, and your face and my face and the sea and whatever it is, all those colors and brightness levels are created by these 3 primary signals. The red and green and blue pixels are driven at various power. And colorimetry is the science of quantifying that and computing things to get it right to what you need. Does that serve as an explanation?
Sure. And can you also give some maybe examples of when you would need to measure color that precisely in something you're building?
So whenever you do something like display, then that's really crucial. But it's also important when you do things like in the medical industry, when you want to illuminate tissue that a surgeon is operating on. Then if that looks just not right, then the surgeon might not be able to differentiate the nerve cell or the nerve from a sinew or something like that. It looks different, but if the illumination is just so bad that the colors don't look like they should, which is the goal of colorimetry, to make colors look like they should, then you have a problem. Or when you are, so there are industries where that's not so important, and the automotive industry, exterior automotive lighting is not that important because, for a headlamp, you just take an LED which is built for an automotive headlamp, and there you go. So I teach a colorimetry class, but I don't have exterior automotive people.
Yeah.
Taking that class too much. So that's something where you don't need it, and you need colorimetry in general interior lighting. So LEDs have for some people have a bad reputation because the white looks white, but the color of things that you put under that light just look horrible, like your skin or a tomato. Or tomato looks brown, your skin looks like that of a dead person, and the meat looks rotten, and we all know that, and it's bad, and it's something that the industry still has to learn. So when you go out now and buy a light bulb, an LED replacement light bulb, you're going to find roughly 9 different numbers on the box, and typically the average person has no clue what they mean.
The foreign language.
It is, the industry has to get better at that,
Yeah.
And to get the color right, they use a term like color temperature, which is actually the temperature of a glowing body, like the 2007 degree, 100 degrees Celsius for an incandescent filament, or the 6500 Kelvin that we have at daylight, which is the temperature of the sun, roughly. So that's one measure, but the other measure that we need is the color rendering index, which tells you how true colors of objects look when you put it under that lamp. And for general illumination, you need that. And for shop illumination, you need, again, something slightly differently. Because for shop illumination, or for illumination of meat in a grocery store, or things like that, it doesn't have to look true. It has to look attractive. Yeah. And that is different from looking true. And there are also ways
maybe you don't want it to look true. Maybe.
Yeah, right. You don't want it to look true because
good.
Yeah, the piece of meat that you're buying has to, from the point of view of the grocery store, has to look good at precisely that moment where you make your buying decision, and not when it's back home on your kitchen table. So there are ways to quantify that.
Yeah.
Also, and to get it right, and then of course we have to translate that into specification of LEDs, and maybe mixing LEDs together and choosing them correctly and driving them correctly. Yeah. So those are the problems which I'm facing and working with.
Awesome. And still try to speak to that audience that doesn't really understand what we do. I'm actually making you just like give me talking points to talk to my clients. So this is what this is. Thank you for that. But you're writing my sales pitch for me. I don't know if you realize that.
No, but that's just great, because sometimes I'm feeling like, how do you call him? Don Quixote? Yeah, ever heard of this guy? So he's very famous in Europe. It's like this tale about the knight Don Quixote, a Spanish knight. Knight, a knight, and he is going on to this, endeavor to fight for something, and in the end he's fighting windmills. And sometimes I feel like this guy fighting windmills and fighting the same, and just it's just like that. So Aaron, please help me spread the word and convince people that there's really it's much more tricky than it looks.
Yes. So what are some other kind of misconceptions, or when someone who's trying to build a product and they're bringing an LED into it, or an illumination aspect, what's a common mistake that you see people making?
The first big mistake is that that these people they don't look beyond the edge of their plates, if you understand what I mean. You are a project manager, or you are a mechanical engineer, or an electrical engineer, or you do thermal engineering, or maybe you are a specialist for manufacturing, or for assembly, or for service. Maybe you're a marketing expert and this kind of thing. And what I found again and again throughout my career in LED systems is that everything depends on everything. So I do this luminaire, okay, and it's like the lamp that goes into a surgery microscope. And then the question is, how much is the optic cost, and how efficient does it have to be? And maybe I can achieve the brightness level that's necessary down there with optics that's actually not too effective, not too efficient. Okay, and then it's cheap and it works well. Except that if I would make it for a little more dollars, like 20% more efficient, then all of a sudden I don't need that much power in the LED, because that's then sufficient to reach the illuminance level. And that lack of heat, which I have to generate up there, may make the difference between passive and active cooling. And by doing a little more on the LED side, I can get rid of active cooling. I don't need a fan, which is probably cheaper, but it's also much more reliable if I don't need a fan. So we need to think about everything. And one mistake that people make in LED projects using LEDs is that they should bring every stakeholder in the beginning of the process to the table. And even if it takes longer and is sometimes a painful process, only when you bring those people to the table in an atmosphere where everybody tries to understand not only his or her own pains, but the pains of all the other ones, and tries to help them by doing some things differently than he or she would normally do. That is the recipe for success of really good projects. And people who don't understand that are going to find out later when it's too late. And that's a common mistake which I observe just too often. So
I see that too all the time. Like, people think that lighting part is easy, or any part of the optics is easy. They can just plug in different pieces, and then they start to build it, and they realize, oh, it's not working like I like it. And then they bring in one of us, but then they've already made the cavity too small for us to build within. Or
yes, ma'am.
There's not enough power that we have.
Yes, ma'am.
So they paint us into a corner, as we say. And then there's less that you can do if you involve experts too late. You've blocked off our ability.
Right now, I'm doing a few projects for companies who want to kill coronavirus with ultraviolet light.
Nice.
And which is great. And I just love to do that. But it's the same thing, these companies, they came to me at a late stage in their project when they thought, we just need a little optics to get things right. And then we are now finding out that optics in this case is where it all starts, because that's the second big mistake that people make. That when you start such a project, it's a very good idea to think things through and look at the first principle laws of physics and engineering which are out there, and understand them and apply them to your project, and then see what the limits of what is possible are and how close are you to them. Because then if something is not possible, it's better to stop early.
Yes.
Yeah. And it sounds so obvious, but sometimes it isn't. And if it's possible, this feasibility analysis kind of thing is taking maybe 5% of the project time, but it's maybe like 70% important. And if you don't spend that time early on to take your time and think things through, and maybe hire people who can help you do that. They don't have to be part of the project. You just have to tell you, don't go there. It doesn't look good there. Go there. It looks much better over there. And that's the kind of thing that people with experience can do if they're willing to help. And I am, and I know that you are. And that's the second big mistake that people that people do when they go on this kind of projects. The third big mistake is that people underestimate the complexity of choosing and driving LEDs. Mm-hmm. So absolutely. Those are my three big, don't do that.
That's great stuff. I know we only have a few minutes left, but can you maybe really quickly run through the different things that you worked on at different stages of your career? Because you've done so much stuff. But
okay, so really quickly, okay. Yeah. So I went to high school. I went to civil service, became a paramedic, and cooked for refugees from Vietnam. Wow. Then I did some odd jobs on the construction site and driving out parcels, and then I started to study physics, which I did. And when I studied physics, I spent much time behind the counter of a bar. And I poured. Actually, I did the estimate once, and I think that I poured roughly 40,000 beers in my career. So I did that, and then when I was done with studying physics, I found that it's a bad time for physicists. Yeah. And that was when the Iron Curtain was coming down around 1990, and they disassembled the National Academy of Sciences in Germany. 20,000 jobless physicists are just out there. So my father is an architect, so I became a real estate developer for 5 years, which is where I found out that I'm just a curious kid and want to be a scientist again. And so I became a scientist again, had the chance to work on solar energy. And first at the University of Munich and as research institute there, and later on with Roland Winston, the founder of non-imaging optics in Chicago, we built a non-tracking, no moving parts, high temperature world record solar collector, only to find out that the world wasn't really ready for it at 1999. Solar energy, just, energy too cheap, and the public awareness just not the way it maybe it isn't even here now.
Yeah.
So it's growing, but not at the right pace, if you ask me. But anyway, we found out that solar energy was over researched and under executed. And a couple of colleagues and I just went back and founded an engineering company for illumination, just turned the light path around. Instead of taking the sunlight and concentrating it, we took it from where it was hot on the lamp, and sent it to where it should be, using basically the same optics that we knew from solar energy. And
but at a time when that type of illumination design wasn't a thing, really.
No, nobody would do it. It was really, we were really odd engineers. It was really a strange thing to do, but we just did it. And to our great luck, it was right at the beginning of the LED revolution, where all of a sudden the photons were so precious that you would basically hand carry them to the target. and that was our niche. And because we were there early and knew our stuff, we had we were just advanced.
Yeah.
And then software like light tools and other programs were coming along and being developed, and so we did that for a while. And then I found that I just have been in academia and being a freelancer and never actually worked for a company that makes something, and never really worked in industry. So I joined Osram, and Osram is one of the large LED manufacturers, and they make things by the billions. So they make many things, and they're also big industry, and big industry has its pros and cons. The pro is that in big industry, you very likely have a real expert for almost everything in the company. For whatever question you have, or wherever you're looking, there's going to be an expert who knows way more than you do. If you're in a small company, that's just not there, because you have the few people on board are just yourself. So that's the difference. But the downside is that the structures are just so fixed and rigid, and there's hierarchy, and there is turf wars, and yeah, and have you been there, Erin?
No, every place I work for, it's been a dream.
Yeah, right. And then there's just also some really just people who are just not very good at what they're doing, not very good at how they're doing it, and just not very nice colleagues.
Yeah.
And that's just that's just like everywhere. And then you think you are in the middle of something really, really bad, and then you find out that behind the facade of this building across the street of this other company, which looks so pretty, it's just different shit flying into different directions, right? So nothing is ever perfect. But Osram was actually great. Osram as a whole is a company that has been making light bulbs, where a train with wagons of quartz sand would come in at the front or at the back, and some other stuff, and something like 270,000 miles of fluorescent tube per year would come out of the front end.
Wow.
Okay, to the moon in a year.
Wow.
And that is Osram. Okay, and they had this LED department, which was this odd branch of the company at some other city, which nobody really knew about in Osram, and they were making the LEDs. And at that time, Osram was that was growing all the time. So when I joined Osram, I was 45. I was the department grandpa. And that was great, because it was just a great time, and it was good from the top down, because everybody was working hard and doing his or her best, but we would be to just stand in the coffee kitchen and drink a coffee. And if the boss, the boss would walk by and would have a minute, he would just stop by and join for a cup of coffee instead of looking like that and go back to your workplace. Huh? We're in Germany. We don't have fun, we work. But he wasn't like that. He just knew that everybody was doing his or her best anyway. Huh? And it was just a great time. And we did some great projects, and we were doing pioneering work of bringing LEDs into monitor backlights. So whatever you watch, it's all LED light now that you see when you look at me on your screen. But at the time, it was cold cathode fluorescent tubes.
Wow.
And we changed that. We the LED industry changed that. Huh? And at that time, I was flying, I don't know how many times, to Japan to work with Sony to make the first really great big red, green, blue direct backlight TV, which is really with outstanding quality until this day.
Wow.
Yeah. So because it is very complex and too expensive for what it is, but the quality is just outstanding, because with red, green, blue LEDs you get saturated colors in the brightness, which you just don't get otherwise. So that was great time. But then
you know more about LEDs than most even illumination optical engineers do. You know them.
I've been there. Yeah. I've seen wafer maps. A wafer map is where the LEDs are on this big wafer, and even before they're cut into pieces, they test each individual LED with a little tip and let it light up, and then they measure voltage and spectrum, like color and brightness, and then they show the values on like a false color map. So it would be the map would be bright where the LEDs are bright, or the map would be green where the voltage is high, stuff like that. So I've seen that. I know so much about LEDs because I had the chance to learn so much in my time at Osram.
Amazing. But then you went on to be back into.
I went back. So I've been at Osram, and at Osram I had a chance to not only work on LEDs, but also be like the global coordinator of the illumination engineers and form a community, which was just great. But when that was working and these 100 people or so were knowing each other and working with each other, I had the feeling that they didn't need me anymore. Aww. My work was but it's just so great. There are two ways to approach things in my mind. Either you do what you do and you're secretive about it, because then you are indispensable. Nobody can fire you. That's the defensive way of doing things. And I always did it the other way around, because if you're indispensable, then they cannot afford to lose you or let you do anything else. So you're basically in your own prison. And I never wanted that. I wanted to create something and create stable structures. And when they were there, they didn't need me anymore, and I could just happily go somewhere else. And they would still love me because nothing broke down when I left. Because I have good friends at Osram until today, because I didn't break anything when I left. I just left a good structure, and then I could just go off and do something else. And that else was ARRI, a company that makes lamp heads and cameras for the movie industry. So basically almost every Oscar-winning movie is being shot with ARRI cameras, and many of them are lit with ARRI lamp heads. So that was great. And as ARRI diversified into the medical industry, where I did the illumination part for a surgery microscope, which is now used across Germany in many hospitals to help people hear again.
Yeah.
By doing surgery on the inner ears and stuff like that. So that's what it. And now, since 2.5 years, I'm a freelancer again, to my great joy. So as I said, we were basically this freelance engineering company like 20 years ago, but now I'm in a different position. Now I have been working hard now to be in a position where I know my stuff with all the experience that I have. And the experience is just something you can only gain over time. So I just couldn't have that at the age of 30, but now I can. And I have so many people know me, so I just can work on the projects on which I like to work, and I can. And one of the things I really enjoy most beyond teaching and writing a book with my friend and colleague Henning Rain.
And the book's coming out soon, and the courses are with Synopsis, right? They can find
the courses are with Synopsis, yeah. And just follow me on LinkedIn, and then you're gonna be up to date on what happens. And but one of the things I really enjoy most is, instead of working on long projects where I can log many hours and make much money that way, what's really exciting for me is to spend those 5% of the total project time with companies to help them avoid these brick walls which are out there, because sometimes it's not easy to see whether something can or cannot be done. And I think it's a great idea for companies who don't have that knowledge on board to hire people like me or you to help them with that understanding, because I'm not shy about sharing what I know. There's just way too much work out there. So I'm not afraid of losing any work because some person doesn't need me anymore. If a client doesn't need me because he has learned enough on the way, then that's a big success for me, because then that person can go on or this company can go on its own again, and I can go ahead and do something else, because there's just so much work out there that the only way of getting it done is to enable more people doing it.
Yes,
I truly believe that.
And it is so satisfying to be able to come in, especially if it's at the beginning of a project, just give you like 1 or 2 hours of expertise.
Absolutely.
And then that's high impact stuff. Like
yes,
the people you're talking to
yeah.
get a lot of value out of it. They're gonna avoid landmines. They're gonna have faster process development. They're gonna have cheaper process development. It's gonna market faster just because they talk to you for an hour. And it just avoids wasting precious energy and money, which is then just bad for everybody. And iterations of development time you can skip by talking to Julius.
Right.
So you can
auto Aaron.
So we are so happy that you are on Auto Engineer right now for the pilot, and if people want to book time directly with you, this is like the leading LED illumination expert in the world. You could talk to him. You can like directly get his advice with a appointment. You just go on there, book it with him, and just follow him on LinkedIn for all the other
go to autoengineer.com and find me and find a time slot, which is actually not difficult, and then just book me. It's just it's like buying something on Amazon, only with more only more rewarding.
And your own company is JMO,
but it's the name of the company. It's just fine. But I don't plan to hire anybody. It's just me.
Right. But if they wanted to contact you there or find your other,
just contact me on LinkedIn or go to jmoptics.de, like Julius Muschaweck optics.de, and that's my website, and you're going to find everything there also.
Beautiful.
All right.
Great. Thank you so much for your time. I know we're running over. It was great having you, Julius.
Thanks for talking to you. It was great. I enjoyed it a lot.
Thanks, me too.
We'll stay in touch.